Thank you. Thank you so much, and thank you for attending this session. I know you had maybe 4 days of hard labor. I'm going to try to show you how your labor could be somewhat simplified with what we've done at Cerebras. So yes, my name is Jean-Philippe Fricker, and as you know, when you go to the US, you need to shorten things, so I go by JP. They even dropped my last name. But I actually went to school at the EPFL, so I'm happy to be in this venue, and thank you so much for giving me the opportunity to talk to you tonight. Cerebras Systems, who are we? So we founded Cerebras with 4 co-founders in 2016, and we went on to building and deploying a new class of computer systems and designed for the purpose of accelerating AI and changing the work of AI. So you'll see how we do that. I'm going to explain a little bit what we had as challenges, but since 2016, I can tell you we grew a little bit. We are now about 350 people. We have offices in Silicon Valley, in San Diego, in Toronto, and in Tokyo. And we now have customers across North America, Asia, and Europe. So it's been quite an adventure. About 5 years ago, we saw something like this. You probably saw this graph many times, but it's actually a key one to understand is that there is an insatiable demand and unprecedented demand for more compute. And so in 5 years, we saw that we needed 40,000 times more compute. You cannot do that with just basically following Moore's law and the traditional design method that one would use to design chips. So we had to embark on something different, and then when you see this trend, you feel like, well, how are we going to solve the next 5 years? Well, we believe we are on a good path for that, and let me show you a little bit of this. So we actually made a very big bet. We said, why do you want to make GPUs on a large silicon wafer and then cut them and then package them and put them in a system, interconnect those systems together, and take all the overhead that you get with it and the hard problem of communicating between them? We said, no, keep them on the same wafer and put about 4 trillion transistors on it. It's about 42,000 square millimeters. And yes, it is this size. We don't cut it. It's one single processor that has actually many cores. We have 900,000 cores on it, and are optimized for sparse linear algebra. It's made with TSMC on a 5-nanometer process. It has about 125 petaflop, it's hard to say anyway, of AI compute capacity. It has a lot of memory. It had 21 petabyte per second of memory bandwidth. This is beyond anything that's done before. And it has a very, very high speed and low latency on-chip fabric of 214 petabit per second. So this is the advantage, right? You take all the cores, many of them, almost 1 million, and you connect them with a very short interconnection on the same chip. You don't have to go in and out of one chip. So let's look at the process of how we made this happen. First of all, the first question that everyone asks, well, you have a large wafer. It's never perfect. You have defects. How do you deal with that? Well, it's impossible to yield a full wafer with 0 defects. Everyone knows that. So today what you do, you test the different chips. The ones that are bad, you mark them, you cut them, you throw them away. The ones that are not so good, you bin them, and you sell them at a lower price. Well, what we did was different. We actually understood where the defects were, and we created an architecture that can deal with those defects. We made it agnostic to those defects by making it programmable, such that if there is a defect, you can work around it. So you have enough bandwidth on the chip, you have enough connectivity between the cores, such that if there is connectivity or a core that doesn't work, you just go around it. So you need to be able to detect this while you're bringing up a wafer, you can test it, you can detect that, you can configure the wafer so that it goes around, and then you can expose to the software layers a pristine wafer that had no defect. You do the same thing in memory, in your SRAM or DRAM today on your computers. That's what's happening even in your cell phone. The flash in there is using a similar concept. We applied it to compute as well. Now, how do we make that? Because the industry has been used to the usual process of repeating the same chip on a wafer and then cutting the chips and then packaging them separately, where we had to convince TSMC that we could actually do something different with them, is to create an interconnection between the various reticles that are lithographically made on a specific wafer, and to convince them that we could actually have interconnections between those reticles. And this is technologically not that hard, but from a process perspective, meaning the logistics of getting the chip made, was pretty hard. And we had to co-design this with their fab. The engineers in their fab had to work closely with our engineers. That was not the entire problem. Once you have a very large chip, the problem is that the chip itself, made of silicon, has a different coefficient of thermal expansion than the rest of the package. The rest of the package is made of typically a printed circuit board that has a low coefficient, coefficient of thermal expansion, while the silicon has a very low one. So if you solder those together, or if you bond them, everything cracks. And I can tell you, we cracked many wafers. We had a lot of mosaics in our labs with wafers that were completely broken. And for that, we had to invent, to compensate for that, we had to invent a connector. And that connector allows us to not only transfer interconnections, signals, to communicate with the wafer, but also to deliver power. And this connector, we had to invent it. No one had it. And we made it such that it can compensate for the thermal expansion of the two devices while maintain connectivity. So this is very hard to do. In addition, it is made harder because we need to carry a lot of power to the chip. It's about 20 kilowatts to one chip, for who knows what that is. It's usually more than your house worth of energy that goes into a single chip. And so to power it, we had to deliver power in a very different way. Today, on your typical CPU or GPU, on your servers, all the power converters are surrounding the chip. They can do that, they have space, and then the printed circuit board brings the power, basically the current, to the chip itself. Because the chip is small, you can reach the center of the chip without too much problem. In our case, the chip being so large, we could not go from the sides and reach the center. So we had to move all those power converters from the surrounding of the chip to the bottom of it and to go to the other side. So I'm talking about power and cooling. So this is on the picture you see here, the bottom section of this picture, you can see how we had to fix the power delivery on the bottom, because today it is done by the sides. For the airflow, it's the same problem. For the airflow, you cannot just blow something on the top across the entire chip. By the time it reaches the other end of the chip, it would be too hot. So you cannot do that with air, you cannot do that with water. So what we did, we used this third dimension. So we moved the power converter from the surrounding of the chip to the bottom of it, and we moved the airflow or water cooling from a laminar, or I would say side-by-side crossing of the chip, to something that is more using or leveraging the third dimension. Both for power delivery and for cooling, we used that third dimension. This was not trivial. No one had this available. No one had a power converter that had to be now much denser to provide the current that we needed. So for who knows about the power here, I told you about 20 kilowatts per wafer, about 1 volt power voltage to the wafer, slightly less. It's about 44,000 amps that you need to carry through that connector. 22,000 this way, 22,000 down. This is unbelievably high density, and no one had the capacity to do that. So we had to invent everything. took us a while, about 3 years to get that done, but we actually got it made. Next, well, you can fit a very large problem on a wafer like this with about 1 million cores and a lot of memory on it. You can fit quite a bit. However, you need to be able to scale. And at some point, the size of the problem doesn't fit on the chip anymore. So we had to create a cluster. And to create a cluster and put multiple of these chips together, we had to do something that's partitioning the system slightly differently than what people typically do. And we had to decouple the memory to the actual compute. And what we're doing, we're disaggregating those two things to be able to scale model and training speed independently. And we do that by streaming weights and gradients in and out of the cluster of our chips. So we start with a chip itself. We then package it into a chassis so we can power it and cool it. Then we add a memory attached to that system, and this allows us to train up to 240 trillion parameters on a single chip, or a single chip packaged in a CS3. Then you can scale that even further, and so you use a special interconnect that can allow us to do a broadcast reduce event for the weights and gradient, while still accessing the external memory. And we can scale almost linearly up to 2,048 nodes. Yeah, we can do that up to that number because we actually have people asking us to build systems of that size. Now let's see what this means, right? It means that you can run data parallel only training on all those CS3s. The weights are broadcast to all CS3, and the gradients are reduced on the way back. And you can achieve multiple system scaling with the same execution model as a single system. This means that programming the entire cluster is as simple as programming one. Same system architecture, same network execution flow, and same software user interface. So this is key, because if you think about cutting experimentation time, if you look at an Nvidia GPT 175 billion model, it took about 20,000 lines of code to create that model, okay? So you need to do a lot of things to make it happen. And I'm sure some people stayed the entire Sunday here trying to do some of this, different scale, but you know how hard it can be to actually do make this large language model work, especially when you have thousands of GPUs. In our case, because this is seen as a single unit, we were able to simplify the abstraction such that you only need to program in Python and 565 lines of code. Now, if you apply the same ratio, it means that what might have taken you 3 hours on Sunday, you could have done it in 5 minutes and be done with it. So this is just on the programming side. I'm not even talking about how fast it executes yet. All right, so if you put this all together, what we've been able to do is to create a very large chip, which we packaged into a chassis. You can see it here, seen from the front, so that we can make it good looking, and you can see a little bit of the inside. Most of it is actually power delivery and cooling. It's water cooled. Part of it is also air cooled. Anyway, I don't want to go into too many details here. We actually deployed it in our own data center in Silicon Valley at first. This is an example. Another example of a larger one. This was Condor Galaxy 1, also in Silicon Valley. And then we started doing a 64-node Condor Galaxy 2 in Stockton, which is actually on a barge on a river, so we can actually take advantage of the water cooling of the river for it. This is a pretty cool installation. And we keep building those and getting better and better at it, and to the point where we're now starting to, with our partner G42, to create an 8 exaflop FP16 AI supercomputer. And this has 56 million AI cores, has 64 systems interconnected together. This is a monster supercomputer, and we are deploying this in Dallas, Texas. So we have so far been able to do 2 complete Condor Galaxy 1 and 2 in Santa Clara and in Stockton, and the next one in Dallas. And there are more to come, I can tell you that. I've been quite busy trying to get the other ones further along. So what do we do with these? Well, here's a good example. Here's an example where, together with G42, we trained a world-leading Arabic LLM. I mean, there are 400 million people that speak Arabic that had no model trained for them, so we were able to do that for them. And this has been adopted by Microsoft as a core LLM offering in the Middle East. And this is available on Azure. This is just one example. Another example is our partnership with Mayo Clinic. There we do a lot of work to help them use the fabulous data set that they have. They have a lot of data, and they finally got to the point where we can use the data in a, I would say, secure manner and controlled manner, so we can actually develop and enhance some of the healthcare tools that rely on large language models. This is a fantastic opportunity, and I hope that in Europe we might have similar endeavors where we can make this type of tool and infrastructure available to you people. I mean, most of you are here that could be actually benefit from this. There are other people that in the energy sector, which is also a big part of the GDP, if you think about it, that started to pay attention to this because they tried to use this and trying to solve some problems, and they got a little bit of speed up with this, actually quite a bit, not 1 order, but 2 orders of magnitude for this, which is impressive, I think. And they were impressed too. And they were also extremely pleased by the ease of use and ease of scalability with this type of solution. Another one is KAUST. KAUST has been borrowing 48 of our systems and doing some experimentation to trying to run some workloads where they found out that it outperformed 37,000 GPUs. So they ran the workload where they were able to outperform the #1 fastest supercomputer in the world. This is eye-opening for some people, especially when you can achieve that by only investing about 1% of the cost of a supercomputer traditionally. So this has been, for us, a tremendous opportunity to grow the company. We can actually order more than we can build today. We have a huge growth ahead of us, but it has been quite challenging in the past too. So we had a lot of good people and talented people that were able to join us to this, and it's been a fantastic adventure. So I want to conclude here. I don't want to make it too long because I know we have a nice aperitif after this, and I'd like to taste some of what is to come. So I don't want to bore you with this. But as a summary, right, we want to enable all to train at ease very large language models. Okay, we see that the models continue to grow in size, exponentially actually, and very few companies can actually afford to train those very, very large models. Today, only the very large 5 or 6 can do that. We want to democratize that and enable anyone to actually get access to this and train this. So that's where Cerebras architecture can shine by making this accessible and not too hard. You don't need to hire 200 engineers to sustain your LLM cluster. That concludes my quick talk on this. I hope you enjoyed it. There are a couple of QR codes here available for you if you want to learn more. I'm happy to answer any questions you might have now or after the talk. Thank you so much.
Good. So after these dizzying numbers, I think we have to sit down. Please.
Yeah, thank you.
And yeah, we have the QR code up. So a lot of things to talk about. First of all, congratulations to this incredible, what seems like an incredible trajectory, at least from the slides you just showed, but we talked a lot also before. And as you said, and I should have said that in the introduction as well, you're an EPFL alumnus. Actually, when was that? I mean, not to put you in a...
Anyone remembers when was that? 97, 95?
97, okay.
I forgot, 93 maybe?
All right. And so
I'm going to stop there. I don't know.
Yeah.
A long time ago.
I mean, it's a bit of an obvious question, but what's you? How to put that?
93, I think.
But how has this kind of? I mean, does this? Because we always talk about this, right? That this situation where we say, oh, you know, we teach the students, but then frankly, the world is changing so fast, right? And in 10 years, who knows what they will do? So I mean, here we are at a 23, 24-year delay in which the world has completely changed. Does your training, what do you think about your training looking back?
So to me, the training has been essential to get where I am. There wasn't a day where I wasn't thinking, oh gosh, I remember that training class, and I remember that professor that I never wanted to listen to. See, it's actually useful now. And it's way later that you realize that. I never liked talking about heat exchange and thermodynamics, and I didn't like that at the time. It turns out it was super useful to actually get this off the ground. So it is, you never know at the time when you learn it. You typically know when you actually use it. And the type of training I got here, I found, was very different than the type of training I could find in people I got the opportunity to hire in the US, where the training had been either way more specialized or too thin, too broad, and not, I would say, up to the task. And so in between, I was able, with my training, to actually span multiple domains. If you think about what we had to do in this particular endeavor, you need to have thermal, you need to have mechanical engineers, you need to have electrical engineers, you need to have software. Well, you need to speak all 4 languages. And they do speak a different language. So being able to interact, understand the problem, and actually facilitate the discussions has been a strength. And so it helped a lot.
Shockingly, the reality is still based on physics, is what you're saying.
Yeah. Physics and very often money. So both are
That's
needed.
another type of energy. Good, so let's dive right into the question. You can see from the ranking itself, there's a sort of one that you probably hear all the time, so let's just get it out of the way, right? So how does this compare, if that's the right word, to Nvidia? But I mean, I guess, obviously, as we all know, the bigger context here is that computation is the main constraint right now. Nvidia is obviously the elephant in the room. What's the dynamic here?
So first of all, just to settle the question and the answer, we don't publish performance results. That's first. Second, I have an anecdote for it. I was not involved directly, but I had the opportunity to listen to what my coworkers said about a customer that came to us. And on the Friday afternoon, they came to us panicked. It's like, we can't train this network, we can't train this. Okay, well, what's happening? Well, we've been working on it. Yeah, we have a team of about 35 people, and we've been working to trying to train this. And since about a year, we cannot make it converge. And I say, okay, well, give us your model and a little bit of data. They gave us the model, a little bit of data. by Sunday afternoon, we got that, and by Tuesday, we had it trained. And we said to the customer, look, is this the problem you're trying to solve? And they were like shocked because they had thousands of GPU available for a year, and they could not make it work. So the problem, I mean, the question is valid. However, it is often not the performance of a given chip that gives you the difference. It's very often, how do you make them work as a cluster, and how do you continue to make them work over time, enough time to make it train completely a given network. Some networks take like 2 or 3 months to train. Well, it's hard to maintain an infrastructure that has failures that happen pretty much every day to make this happen. So yes, performance is one thing, and for a given workload, I can show you some numbers that are like 236 times in one of the slides I mentioned, right? Exactly. In some other slides, we've had some opportunities beyond 1,000 times faster, but for other workload, it is less. It's more single-digit improvement. It all depends on the workload. But for the large language model, I can tell you, we beat them anytime.
Okay. There are a couple of questions about cost that I want to somehow merge also in the interest of time. So cost, obviously, in terms of cost for a chip, cost also in terms of energy, right? What's the energy use of these things? And then cost, obviously, also in terms of the software framework. I mean, people think about, of course, buying chips, but then also there's the development around it. Nvidia obviously has the mode with CUDA, so how does this, can you walk us briefly through the...
Cost of the chip, we don't disclose it, but it is actually quite cheaper to do this, and it all depends compared to the performance you get. So if you have a high performance on our chip, suddenly, well, Nvidia might look like extremely expensive compared to ours. In some other cases, it's somewhat in the vicinity, but we tend to be cheaper in many aspects because we outperform them. So you need fewer of their entities to do that. Cost of the chip is a portion of the entire system, and it is not the most expensive part in the system. Usually the power delivery is what costs the most. Then the question about software, 80% of the company was for a long time software engineers. And yeah, you might think that doing hardware is hard. Doing software is harder and takes a lot more effort and patience and smart people. And so we were lucky. We could attract smart people to help us in this. And we have a fantastic team that has been able to abstract the complexity of such a chip, such that when you program it, you can actually use PyTorch, and you don't have to use all the other assembly languages or other weird languages that you need to put it together. And we abstract all the complexity of the cluster, so you can see this entire supercomputer as a single, I'd say single GPU-like component.
Okay.
But we had to ourselves take on that burden and abstracted it for all the layers, from testing every individual chip all the way to having a tool that allows you to debug it. And so, yeah.
Yeah, you did it. So last question. So you said in the beginning, you made a big bet, right? And you made a bet on this particular architecture, on this future. Can you, probably not fully disclose, but can you speculate a bit on the bets that you're making now for the next 5 years? Because one is curious, right? Do you expect this to continue and your architecture to remain the same, or are you making new bets because it's worked so well for you?
So it feels to me that the bet of having a wafer-scale engine that is a wafer that is not singulated, that is not reconstructed, as some might do, was the right choice. We see at every generation, we ask ourselves, is this really what we should do? Should we continue to do it this way? And yes, it has been the way to outperform all the other architectures. Going forward, you might say, well, what do you do now? You reach the size of a wafer. Well, there are other ways to pack even more compute that we can think about. How you optimize the amount of memory, how do you optimize the I/O, and how do you optimize power and cooling for such an architecture. So yes, I see us being able to keep up. It's going to be hard for everyone to do that, but I think we are well positioned for it.
Well positioned. Well, I said yesterday, one of the biggest compliments people can give us at AMLD is when they come back and say, the first time I heard about this was at AMLD. I'm sure that's probably one of them, because your trajectory is amazing. If we can just extrapolate it a little bit, then it's an absolutely crazy success story in the making.
Yeah, especially if you think about the time it took us to just convince our investor that, yes, stay with us another year, please. We just failed for 2 years to make anything, so please go ahead, have confidence in us. They kept going with us, and now for the last 3 years, 4 now even, the company has grown, as I showed you, from just packaging one chassis into now deploying multiple data centers across the world, actually. We are growing, and so it's a fantastic place to be, where there is such a high demand, and we have a product and a solution that is well tailored for that market. So it's awesome.
Well, congratulations, and it's been a huge privilege to have you here. And as you said, you'll be around also for the apéro for further discussion, the questions that I'm sure you will get. Thank you so much, JP.
Thank you so much.
Thank you.
Thank you.